Thursday. It's your second test. And there is the study guide. So the test is going to cover it's always the last switch. Test is going to cover synthesis based on syntax, and what I mean by that is certain syntax produces a certain type of circuitry. There will be questions on tasks and functions, different aspects of inference versus instantiation, a little bit on system tasks, like we had file I/O, system tasks, test bench construction, coding style recommendations. Lattice, for example, had a recommendation on what encoding you should use for finite state machine. Xilinx had something different. And then value change stone files. We'll need a Scantron to record your answers. Don't forget a pencil. I've had students in the past use a pen. The machine doesn't read pen. And you may use any electronic device capable of reading PDFs during the exam. Any questions on that? Okay, so we were working our way through the Synopsys User's Guide for synthesis. And again, I want to emphasize the fact that whatever synthesizer you actually wind up using, it is really imperative that you read the user's guide, find out what the capabilities are, and what some of the selectable options are. The next topic that we're going to go into after this is timing and timing closure. And one of the things that will be brought out very clearly in one rather ugly flowchart is when you try to achieve timing closure. Silly, what was timing closure? What was the definition of that? What's the significance of timing closure?
Timing constraints.
I'm sorry?
You're meeting your timing requirements.
Okay, you meet all your timing requirements. The two biggest ways that you have of trying to achieve timing closure that is under your control is recoding and different synthesizer options. So it's imperative that you understand for your synthesizer what options are available to you, because it's a valuable tool to achieving timing closure. Okay. So on page 699, they talk about working with gated clocks, and they show some examples on page 6-100. Here are a couple different gated clock circuits, and again, the issue here is your clock is running continuously. It's a free-running oscillator. So if you don't gate that clock signal, registers will respond and update their output on every clock pulse, and that may not be what you want. So you have some sort of gate signal that controls when the clock signal actually gets applied to the clock input on the register. So in this case, A and B both have to be logic 1s in order to get clock pulses to this register. Here is the preferred solution, and this is the way that you should code your Verilog modules if you need a gated clock, is the clock gets applied to the clock input of the register, but you have this feedback to a multiplexer, and your gated signals for the clock now drive the select line. So you either have data input appearing on the D input here, or the current output, so that there will be no change. In a previous video that we looked at, they talked about, and we had talked about this on managing complexity, about having a very distinct data path and control path in your design. When you do this, you have moved your clock enable signals from the control path into the data path, and that leads to a more efficient design. Design planning and optimization. This uses a tool called Design Planner. This talks about pin assignments. To show you the effect of pin assignments, and you'll see an example later on when we talk about timing constraints. If I have my logic on one side of the chip, and the output of that, which goes to output pins, are on pins assigned on the opposite side of the chip, you have rather long traces. That's not a good placement. So one of the things that you are able to do through some of these tools like Design Planner is actually move something around inside the FPGA. So it's still implemented the same way, it's just implemented in a different subsection of the FPGA fabric, and that can lead to improved timing. So in some cases, there's nothing wrong with your design. This is a placement and route issue where you need to move things around on the FPGA fabric to achieve better timing. So on pin assignments, they specifically talk about methods for specifying pin assignments, using the Design Plan Editor to do that. Display rat nesting and clock pins are also discussed in this section. Chapter 8 will talk about vendor-specific optimizations, which is, of course, something that you should specifically focus in on. Synopsys is a third-party supplier, so their synthesizer needs to work with FPGAs from Actel and Xilinx and so forth. So they talk about things in this chapter about passing information to placement and routing tools, generating specific output, and then they talk about these for FPGA vendors and specific things that you should look for. As an example, working with the Xilinx designs, they will have sections for instantiating CoreGen cores. We talked about that. Clock buffers, re-optimizing with EDEF files, and so forth. They talk about, for example, on critical paths, you may want to use this particular synthesis attribute for I/O pins, etc. On instantiating CoreGen cores, they talk about creating black boxes. We talked about black box synthesis before. working with Tcl scripts. Everybody familiar with the term script? A script is, I guess in Microsoft land, they call those batch files. It's an ASCII file that has a series of commands. So rather than you typing in every individual command to do a synthesis, you will put all those commands into a script file. And then from a command line, all you do is you type in the name of the script, and there may be some parameters that you can add on that same command line. You hit return, and automatically it starts cycling through the commands in your script file. Tcl is how that's pronounced. That stands for Tool Command Language, which is a very popular scripting language. And of course, there's an associated document with that that will tell you the different syntax of Tcl commands. But examples of things that you would put in the Tcl file is, you recall that when you use that GUI to do your synthesis, one of the steps you had to do was go to a drop-down menu and select your FPGA. Well, there will be a Tcl command in there that says, this is the FPGA I want to use in this particular synthesis. Your pin assignments can be put into the Tcl script file. Now, as you can imagine, when you went through that GUI, it took you a little bit to work your way through all the menus and do all of the things that you needed to do to get that bit file. So you can imagine that the Tcl file itself has got a lot of commands in it. And if you were going to type those out individually, that might take you some time to construct the Tcl file. When we get to timing closure, we're going to see that to get timing closure, you have to resynthesize a number of times with different synthesizer options, with recoding that you've done, so that Tcl file would have to be executed many times. So you would think, well, gee, this may be a long file, but I only have to type those in once. And you may not be certain that you've got all the commands you should have in there to properly do the synthesis. Well, you have a way out. Generating the job script, work through a synthesis session. The first time you do synthesis, use the GUI. You're going to get all the steps necessary to generate your bit file. And one of the things that will come out of that you can store is the Tcl file. So that's how you would get your initial Tcl file. Then from there, you're just doing editing. If you're going to change a pin assignment or you want to change some timing parameter or whatever, you're just editing a file. But you don't have to worry about generating the initial script file. Use the GUI and let it generate the Tcl file for you. And then in subsequent synthesis runs, go to a command line at a terminal or whatever and use the Tcl script file. Just to show you some of the things that you can do in a Tcl file, and I thought this one was particularly interesting. You could create a for each loop that runs through each option in the list. So for example, if I wanted to try different clock frequencies, I can set up this Tcl command and it will cycle through each one of those and produce an output. So there's really some clever things that you can do with these script files. Now I want to show you a document that I put on D2L. We talked about synthesis directives and synthesis attributes. So there's an entire manual. Is this it? No. Maybe. Okay. That tells you what the different attributes are. And the first thing I want to show you here is the difference between a synthesis attribute and a synthesis directive. Attributes control mapping optimizations, directives control compiler optimizations. And that's the difference. Remember we talked about when you implement a design, there were 3 phases. What were the 3 phases? If you hint, the first one was mapping.
Mapping, placing, and routing.
Placement and routing. During the mapping phase, that's where your attributes come into play. The directives then control the compiler optimizations, the rest of the synthesis process. I want to show you an example of one in here. Synthesis encoding. This overrides the default finite state machine compiler encoding for state machines and applies the specific encoding. It is through this attribute in your source code that you would define how you want the finite state machine implemented. And here are different values that you can use for those attributes. One hot, gray, sequential, and safe. And original, this respects the encoding you set, but okay. Do you need to describe the safe? It says this implements the state machine in default encoding and adds reset logic to force the state machine to a known state if it reaches an invalid state. What might cause a finite state machine to enter an invalid state? Has something to do with metastability.
If it gets into a position it's not supposed to get into logically somehow?
Well, that's what an invalid state is. You recall on a finite state machine you have at least one input, other than clock not being considered an input. You have one other input. That input may be coming from the external world. And so it is not synced in any way to your clock. What happens if that input comes in and it does not satisfy the setup time before you get a clock? You could enter a metastable state, and you may even wind up, when it eventually settles down into something, which it eventually will, into an invalid state. So in safe, there is a reset state that if it enters into an invalid state, a state that you have not defined in a case statement, for example, it will take you into that safe state. So here is the example of how you would use this particular synthesis attribute. You recall that in the finite state machine, you always had a declaration like this that contained the current state that you were in. This would be for a more finite state machine. There's your synthesis attribute, and you notice that you can choose a couple of values in here. In this case, they wanted it safe, and they wanted a gray code encoding of the states. Okay. The next topic is timing, and there's a couple of videos that I want to show you. And then I'm going to go into, rather than show you the third video, I was able to obtain a copy of the slides, and I pared that down to cover just the essential points when we want to talk about timing closure. But the videos are particularly good on timing constraints. What type of timing constraints there are, and how do you define them? At the very beginning of this course, I had a brief section I showed you, objectives of the course. And I said that in most courses like this, they teach you a hardware description language and then spend a lot of time having you do science fair type projects, et cetera, so that you can simulate designs and whoopee. But there's a lot that is left out. One of the things that is almost entirely left out is timing. And when you look at the time spent taking a FPGA product from inception to turn it over to manufacturing, you would be shocked at the amount of time that you're going to spend trying to overcome timing violations. It's a tremendous amount of time. And when we get to the timing closure portion of the lecture, you'll see that when you see this humongous flow chart showing you all the things you have to do to achieve timing closure. And so if you don't have at least a firm idea of timing issues associated with FPGA design, you're actually got a big hole in the background that you should have on FPGA development. So I'm on the PC.
My name is Frank Nelson. I'll be your instructor for this module. This module introduces the primary timing constraints used by all Xilinx customers, the global timing constraints. Please note that this topic is included as part of the Essentials of FPGA Design course. Timing constraints are fundamental and essential for users to get their performance objectives met. However, the use of global timing constraints is only the first step. You will also need to use path-specific timing constraints, which is a part of the Designing for Performance course. We recommend that you take the time to attend these courses to complete your learning and help make your design successful. After completing this module, you'll be...
I want to make a comment about that. Xilinx is pretty good, and so are the other FPGA manufacturers, in providing typically one day, sometimes they're more depending on the topic, training sessions where you can come to their facilities and they will hold courses where they will talk about various aspects for ASIC development and FPGA development, etc. If you're working for a company, you should, whenever possible, convince your supervisor to allow you to attend these. You usually get free donuts, which is always a big plus. Plus you get out of work for a day or so. But they really pay off because they're very focused training sessions, and they're usually hand-on. They'll have lectures and then they'll have some sort of lab associated with it so that you can get to know some of these concepts. And he makes a comment in here that some of his customers re-attend some of these conferences or workshops every 3 or 4 years because they are constantly being updated. So if you find out that your company is using a particular company's FPGA, you ought to investigate what type of courses and workshops they provide, because they can really cut down the learning curve associated with getting a design up and running.
To apply global timing constraints to a simple synchronous design. And you'll be able to make those constraints with the Xilinx Constraints Editor. This module is important if you're going to be attempting to complete any Xilinx FPGA design. So be sure you understand and follow the suggestions made in this module. In this example, we took a small and simple design and implemented it without the use of any timing constraints or pin assignments. This is shown on the left. Note the logical structure of the placement of logic and the placement of the I/O pins. The implementation tools do a good job of placing and writing the design without using timing constraints. From this example, you can see that the logic is grouped close together in the middle to provide a good internal frequency and minimize the clock skew. Likewise, the I/O pins are placed together so that pins from the same component end up next to each other. This makes the most sense since they are related. Note that the tools do not anticipate any ground balance problems. The tools do not know when the signals will be toggled or how many signals may change simultaneously. It is left to the designer to be certain that you try to disperse switching outputs that are switching simultaneously to help avoid any problems with ground balance. To help with that, the Architecture Wizard and PinAhead recording learning module discuss how to place I/O pins efficiently so you reduce the risk of creating a ground balance problem. Now, on the right-hand side, the same design was implemented with global timing constraints. This required the use of input, output, and internal timing constraints, which forced the implementation tools to move the logic closer to the I/O pins to improve on-chip and off-chip timing. Now note that the logic is placed closer to the I/O pins due to the input and output timing constraints. Timing constraints are used to communicate performance objectives to the implementation tools for software, which in turn is used to place and route the design such that the design will meet your timing objectives. When timing constraints are used, the placement and routing solution can be very different. In this case, the pin placement is almost identical to the original implementation without using timing constraints. However, the placement of the logic is significantly different.
Okay, so without the timing constraints, the place and route tools try to optimize the timing for the design without regard to the I/O. You'll notice in this design, they compromise somewhat on the internal timing to get better I/O timing, because you did put in timing constraints. So you'll notice that the input and output pin placement, which as he pointed out were the same, the logic got moved closer to that. So you gave up a little bit on internal timing, but got improved I/O timing, because all of that was taken into consideration. This dramatically shows you the effect of what happens in placement and routing when you do put in timing constraints.
The net result is a faster performing design at the expense of a slightly longer implementation time. Timing constraints are used to define your performance objectives. Tight timing constraints will increase your compile time, depending on the speed of your device and design. Unrealistic timing constraints, often called over-constrained, will cause the implementation tools to stop. If your design does not proceed through map and you receive a message warning you of an unrealistic constraint, you will need to use your synthesis report or the post-map static timing report to determine whether your constraints are realistic. After implementing, review the post-place and route static timing report to determine whether your performance objectives were met.
And we'll
If the
see
timing
some of
constraints
those.
were not met, use the timing analyzer utility from the ISE software to generate a timing report. This will enable you to determine the cause of the timing failure. Causes can include many possible reasons, such as too many logic levels, that is Ludson series, which is caused by poor HDL coding, perhaps a high fan-out net delay, or even a need to pipeline the data path are some prime examples of causes of the tools not being able to meet your timing objectives. Now, you can learn more about interpreting timing reports in the Achieving Timing Closure module in the Designing for Performance course. Likewise, the same course shows you how to use the timing analyzer and all of its features. Before we proceed to introduce you to the global timing constraints and the delay paths they cover, it's very important that you understand the possible path endpoints you can have. Once you start to understand how the implementation tools look at your design in terms of path endpoints, making the best timing constraints is very easy. While global timing constraints are very simple, understanding possible path endpoints is useful when you learn about path-specific timing constraints. Like global constraints, path-specific constraints are important to properly communicate your timing objectives to the implementation tools. Simply put, path endpoints are I/O paths and synchronous elements. Synchronous elements can include flip-flops, latches, RAMs, DSP slices, and shift register LUT resources. Note all the synchronous elements, of course, are synchronous because, of course, they have a clock port. Path endpoints do not include LUTs, nets, or any other purely asynchronous. Think about improving the timing of your design. Remember that you are first grouping path endpoints, and these are the only types of path endpoints that can be grouped. Again, that's I/O paths and synchronous elements. Once path endpoints are grouped, and these are grouped easily by global timing constraints, the next step is to specify a timing objective between the groups. Global timing constraints are easy to make because they save you from grouping path endpoints. This means you don't have to be specific about which path endpoints are part of a specific group. As you will see, that is because global timing constraints group elements based simply on the clock signal that is connected to those synchronous elements.
This is your first constraint.
There are 3 global timing constraints. The first, and most significant because it covers 80+% of internal delay paths, is the period constraint. The elements it groups are simply the synchronous elements it's attached to. In this example, there is 1 clock, and it attaches to 5 flip-flops. This defines these flip-flops as both a group of sources and a separate group of destinations. So in this example, there would be 3 delay paths that would be constrained because they would cover the paths that go from the group of sources to the group of destinations, which happens to be the same group of flip-flops. As you can see, the delay paths cover from flip-flop 1 to 2, flip-flop 2 to 3, and flip-flop 4 to 5. This should also teach you that there is no relationship between the number of path endpoints and the number of constrained paths. The number of path endpoints and delay paths is simply design dependent, and that can be very complex or it can be very simple. It'll just depend on your design. Now, once you have made your timing constraints, the constraints editor will store them in your UCF file. That is your user constraints file. This is the same file your pin assignments will be placed. The implementation tools will then use your timing constraints to manipulate the place and route solutions so that your design will meet all of your timing objectives. This requires the implementation tools to be very sophisticated. That's because accurately measuring an interim delay is not just a huge database of static numbers. The implementation tools also must be able to properly factor in the clock skew associated with the ClockNet's internal routing delays. The tools also need to be aware from your netlist that not all of your synchronous elements will be toggled on the same clock edge, so that has to be anticipated. And it also has to be aware of your defined clock's duty cycle and the input clock jitter. When you couple that jitter with the performance characteristics of a DCM or PLL you may be using to derive a clock kernel signal, then suddenly that calculation is a little more complex. So all of these factors are built into the implementation tools when completing a static timing analysis, and that's done for each iteration. Remember, you may have to do multiple iterations depending upon your speed grade and how tight your timing objectives are. Don't forget that all this may have to be completed many, many times to find a place and route solution that will meet all your timing needs. Suddenly, now you have a great deal of respect for the ISE software. In the end, the point is that these tools are built to try and anticipate many of the factors that go into affecting the internal delays of your design. You should have some confidence now that this software performs a lot of hard, accurate work on your behalf.
So the period constraint just says, hey, this is for these nets, this must be the period of the clock cycle for them?
Correct. Oh, let's watch chapter 2. Well, one of these days I'll be trainable and be able to figure this out.
In this example, we're just trying to show you how the tools recognize that you're triggering off the negative edge of your clock. So here we have a clock with a 10 nanosecond period constraint, and the first flip-flop is toggled off the rising edge, while the second flip-flop is toggled off the negative edge. So, as you have probably already figured out, this means that the constrained delay path should now be constrained to 10 nanoseconds, but 5 nanoseconds. So what happens is the tools will use the 5 nanoseconds as a constraint, and after implementation is completed, you can generate a time report.
Does everybody see why the period constraint here is 5 nanoseconds and not 10 nanoseconds?
Because the clock is.
Because it's a 50% duty cycle, 10 nanosecond, period. The first flip-flop is off the leading edge, the other one is off the trailing edge. The time difference between the leading edge and the trailing edge is 5 nanoseconds. So you have a 5 nanosecond period constraint, not a 10 nanosecond for this particular design.
It will report the delay path as being constrained to 5 nanoseconds, not 10. No big deal, except if you did not realize that you were toggling off the negative edge, this might pleasantly surprise you if the tools were thinking about your design and trying to anticipate a problem. The constraints editor allows you to enter in an input clock jitter. This enables the implementation tools to plan the place and route appropriately so the jitter can be tolerated. But don't forget, if you have excessive input clock jitter, the newest FPGAs have dedicated PLLs on board inside the FPGA to help you remove it. To learn more about the FPGA's clocking resources jitter characteristic, check your FPGA user guide and look at the specifications. Now, the Architecture Wizard has a jitter calculator that allows you to know how much jitter a PLL or a DCM will put on your clock. This value should then be placed on the clock when you make your period constraint. As you know, this clock uncertainty is automatically subtracted from the period constraint setup paths. The clock uncertainty is automatically added to the period constraint's hold paths.
These are your other two
The offset
constraints.
constraints cover paths from input paths to synchronous elements, that is the offset in, and synchronous elements to output paths, and that is called the offset out constraint. Just as
Okay, so there's the three timing constraints that Xilinx allows you to do. One is the period constraint. The second one is offset in, and the last one is offset out. And look at how they're defined. Offset in is from an I/O pin to the input of the first registered element, and anything in between. Offset out is the time delay from the last register output to an output pin. So you're going to specify, if you will, input propagation delay, output propagation delay, and a period constraint. And then the timing report that you get, once you specify what your constraints are, it will generate a separate entry for every timing violation it found. And we're going to take a look at some of those shortly.
The period constraint, the global offset constraints are associated with the clock net, which automatically groups the synchronous elements that will be considered as path endpoints. So in this example, we have one clock signal. It drives the same 5 flip-flops. The offset in constraint covers the 9 input paths. Note that the input bus is 8 bits wide, and the offset out constraint will cover the 3 output paths. Now, a lot of people don't easily understand how there can be 3 output paths. Well, it's simple, really. The 2 source flip-flops have 3 different ways to get to 2 output pins. And as I mentioned earlier, the number of paths will vary greatly by the behavior of design. Likewise, the input paths covered by the offset in constraint is usually mistaken because an input bus of 8 bits is used in this case. They just basically don't see the big fat wire, but you probably figured that out now. Also, you should note that even after specifying an offset in, an offset out, and a period constraint, it is still possible to have unconstrained delay paths, such as purely combinatorial paths that you see in this example. Remember that the offset in and out constraints do not cover paths between synchronous elements, and they do not cover paths that are purely combinatorial. This example shows how the tools use the clock distribution delay to calculate the effective offset in and offset out delay. As you know, the clock delay is a significant factor in the effective delay and cannot be ignored. Because the input data path and clock path are in parallel for input paths, the tools subtract the clock distribution delay from each input path. Likewise, because the output data path and the clock path are in series for output paths, the tools will add the clock distribution delay to each output path. Therefore, having a positive clock distribution delay helps your input times, but it hurts your output times. To compensate, Xilinx FPGAs include a delay lock loop and or a PLL for your chosen device that will remove the clock distribution delays from your input and output paths. These resources are very important for good chip-to-chip timing. Remember that the PLL and DLL resources do not remove clock skew. The DLL only compensates for the clock distribution delay. The global routing resources are designed to minimize the clock skew, but they cannot remove it entirely. This slide shows an example from a timing report generated for an offset out constraint. As you know, this report can be generated when you use the timing analyzer utility. And again, as you mentioned, we cover the timing analyzer as part of the Designing for Performance course. You may recall that the offset out constraint covers output paths.
I'm not sure how well you can see this, but up here it says that, in fact, I can't even read that. I think it says the minimum allowable offset is 2.449 nanoseconds. That's your timing constraint. And in this particular path, it found a data path delay of something over 3 nanoseconds, and it found a clock path delay of over 4.6 nanoseconds. It also tells you here the levels of logic. Each time you have to go through a LUT, you've gone through one level of logic. So in the case of the clock delay, they went through 2 LUTs to get to the device.
From synchronous elements to output pins. In this case, we use an offset out constraint of 16 nanoseconds. This constraint covers the effective output path, which, as I just mentioned, is the clock path delay plus the data path delay. In this case, please note this is highlighted in the red square. The clock path to this register is 4.6 nanoseconds, and the data path was 3.8 nanoseconds, which makes an effective delay of 8.4 nanoseconds, which is highlighted in the red circle, which is what the tools found for the longest constraint path to be constrained by the offset out constraint. So this is verification that the implementation tools automatically account for the clock distribution delay for each data path. They provide the most accurate timing information possible, including taking into account the clock jitter. They use the jitter defined on the associated period constraint. Because the tools account for the clock distribution delay, you can specify your pin-to-pin timing goals without knowing what the internal clock distribution delay will be. Well, now we wanted to give you a chance to test your knowledge of the basic global constraints and what paths.
Okay. So let's apply your knowledge. Which paths are constrained by a period constraint on clock 1?
PAD1, the PADA.
The PADA path. And which by a period constraint on clock 2?
PADAB.
PADB. Let's see if that's correct.
Covered. This is, again, a very simple example, certainly not very realistic, but I wanted to make sure you had a chance to think of another example. In this case, I based the questions on some of the most common questions I get. So this example contains 2 clock nets, which is important because this means that if you were constraining this design, you would probably use a period, an offset in, and an offset out for each clock domain to properly constrain the design. The first clock, clock 1, has 2 synchronous elements, which is probably the first question you would ask. How many synchronous elements are in each clock domain? Because that will dictate how many paths will be constrained. In this case, the period constraint will cover 1 path, from the flip-flop to the latch. The second clock, clock 2, has only 1 synchronous element, so a period constraint on this clock would not actually constrain any paths. This is again because the tools do not have a path from a source to a destination synchronous element.
Okay, does everybody see why there's a constraint on clock 1 but not on clock 2? Clock 1, you've got, well, let's put it this way. To constrain a clock path, you have to have 2 or more synchronous elements. You do in the clock 1 path because you have a flip-flop through a 1 or more LUTs into a latch, and the latch enable and the clock input on the flip-flop are all driven by clock 1. But you only have a single synchronous element for clock 2, so the period constraint may not affect this path. Clock 2 may go to drive other paths where you do have multiple registers, so it may be constrained elsewhere, but not here.
Now we want to introduce you to the Xilinx Constraints Editor, so you can get an idea about how you're going to be making your global timing constraints on your design. To start the Constraints Editor, double-click the Create Timing Constraints button in the Processes window of the ISE software. If you don't see this button, expand the User Constraints button to then see the Create Timing Constraints button. After the Constraints Editor opens, there is a Constraints Type window in the upper left-hand corner of the GUI. This is highlighted in red in this example. To make your global timing constraints, double-click the Clock Domains button. This will open the Create Timing Constraints GUI, which automatically reads from your design's netlist. All the clock signals and I/O pins from your design will automatically be read. So as you can see from this screenshot, the input clock signal has a name of clock_pin. This then propagates a group name, or in this case, a clock time name of clock_pin. So it borrows that name. That makes sense. That makes it easier to make your constraints. The time spec name is automatically given as TS_clock_pin, and that's just a label. And in fact, all they did was take that group name and just put in TS_ in front of it. And the TS will stand for timing specification. This makes it easier later on when you're reading your UCF contents to actually identify the timing constraints because they have the TS in front of them. So this is the label the timing constraints will be given in your UCF file. So to make a period constraint, you just right-click on the constraint that has already been made and click on Edit Constraint. To make a new period constraint, you right-click in the Create Timing Constraints window and select Create Constraint. The constraint entered will have default units of nanoseconds and assume a 50-50 duty cycle. But this can be modified with the GUI. As constraints are made for the Constraints Editor, they are added to the User Constraints file. And then you can use any text editor to edit the UCF Or again, come back to the constraints editor and modify the constraints for this utility.
So what you do is you,
Many designers keep their timing constraints in a separate
let me go back to this real quick. So what you put in is the clock name, the period that you want, the duty cycle, it defaults to 50, but you can select something else. And on edge, you put in high or low, whether you want that clock to be positive or negative edge triggered.
and modify the constraints for this utility. Many designers keep their timing constraints in a separate UCF file from their pin assignments, area constraints, and placement constraints. This allows the designer to keep all of their fixed constraints, that is, their pin assignments and placement constraints, in one location, and then never modify the contents after they have implemented those constraints. So you see, it's kind of human nature. They like to keep their timing constraints separate because they end up frequently editing their timing constraints file. And this makes debugging a little easier. So to help with this, the Xilinx Constraints Editor allows you to select a different constraints file to be edited and modified with the utility. And if you're
So there's kind of a design hint. Things like pin assignments aren't going to change. So keep those in a separate user constraint file. And then just have a constraint file for your timing. It's a smaller file to deal with. Easier to debug, easier to maintain.
whichever constraints file you have, you can use the drop-down arrow to make sure that the tools find all of your design's constraints files.
What's next? A 10-minute break.